Hello, dear viewers. Today we will discuss about the difference between the OSI and TCP/IP model, and after that we will discuss about addressing of network devices. Difference between OSI and TCP/IP model. First we will start with OSI model. OSI model, the Open System Interconnection Model, is a layered framework for the design of network systems that allows communication between all types of computer systems. It consists of 7 layers: physical layer, data link layer, network layer, transport layer, session layer, presentation layer and application layer. Sometimes OSI model is called as vertical approach. It defines the services, interfaces and protocols very clearly and makes a clear distinction between them. In OSI model, the protocols came after the model was described. In OSI model, each layer performs specific functions. The OSI model supports both connectionless and connection oriented communication in the network layer, but only connection oriented communication in the transport layer. It has a problem of protocol filtering into a model. The protocols are better hidden and can be easily replaced as the technology changes. Now, TCP/IP model. The TCP/IP model stack is a de facto standard in networking. TCP/IP model is an open standard, is really been implemented in practice. TCP/IP model has 4 layers: physical and data link layer, network layer, transport layer, application layer. In TCP/IP, different protocols may be defined within a layer, each performing different functions. Sometimes it is called vertical approach. TCP/IP model is an implementation of OSI model. TCP/IP model is defined after the advent of internet. TCP/IP model does not clearly distinguish between services, interval and protocols. In TCP/IP model, the protocols came first and the model was really just a description of existing protocols. In TCP/IP model, the protocols are not hidden. The TCP/IP model supports both connection and connection oriented communication in transport layer. In TCP/IP, it is not easy to replace the protocols. In this model, there is no session layer. Characteristics are provided by transport layer. In TCP/IP, there is no presentation layer. Characteristics are provided by application layer. Now we will discuss about addressing. First we will start with physical addresses. The physical address is also known as link address. The address of a node is defined by its LAN or WAN. It is lowest level address. The physical address uniquely identifies computer on the network. It is hexadecimal address hard coded into the network card. The size and format of the physical address vary depending on the network. For example, Ethernet uses a 6-byte physical address that is imprinted on the NIC. Physical address is also known as MAC address. A MAC address is most often represented in hexadecimal using one of the 2 accepted formats. For example, 00 full colon 43 full colon AB full colon F2 full colon 32 full colon 13. Second example, 0043 dot ABF2.3213. The first 6 hexadecimal digits of a MAC address identify the manufacturer of the physical network interface and referred to as the OUI, Organizational Unique Identifier. The last 6 digits uniquely identify the host itself and are referred to as the host ID. Obtaining your computer's physical address. Click on Start button and then select Run from menu. Type CMD and press Enter. Then type ipconfig/all and press Enter. Then copy the physical address exactly as it appears. For example, in this case, physical address 00-19-D1-A4-F6-8E. For example, in this figure, a node with physical address 10 sends a frame to a node with physical address 87. The two nodes are connected by a link bus topology LAN as the figure shows. The computer with physical address 10 is the sender and the computer with the physical address 87 is the receiver. Logical addressing. As we know that there is a host to host communication at the network layer and a computer needs to communicate with another computer somewhere in the world. The computers usually communicate through internet. For this level of communication, we need a global addressing scheme called logical addressing. The logical addressing is also known as IP addressing. An IP address is a 32-bit address that uniquely and universally defines the connection of a device, for example, a computer or a router to the internet. It is a numeric identifier that is assigned to each machine on an IP network. IPv4 addresses are unique. They are unique in the sense that each address defines one and only one connection to the internet. Two devices on the internet can never have the same address at the same time. If a device operating at the network layer has M connections to the internet, it needs to have M addresses. It designates the specific location of a device on the network. An IP address is a software address, not a hardware address. The hardware address is coded on a network interface card and is used for finding local host on local network. IP addressing is used to provide communication between hosts on one network to hosts on different network if the hosts are on different LANs. Few terms related to the IP addresses are octet. An octet is made up of 8 bits and is just an 8-bit ordinary binary number. Network address. This is the designation of the address used in routing to send packets to a remote network. For example, 10.0.0.0. Next, 192.168.10.0 is a network address. Broadcast addressed. The broadcast that is used by application and host to send information to all nodes on a network is called broadcast address. For example, 255.255.255.255. Second, 10.255.255.255, etc. Address space. An address space is the total number of addresses used by the protocol. If a protocol uses n bits to define an address, the address space is 2n, because each bit can have two different values 0 or 1, and n bits can have 2n values. IPv4 uses 32 bit addresses, which means that the addresses space is 232 or 4294,967,296, more than 4 billion. This means that if there were no restrictions, more than 4 billion devices could be connected to the internet. Notations. There are two notations that are used to show an IP address: binary notation and decimal dotted notation. 1. Binary notation. In this type of notation, the IP address is denoted in the form of 32 bits. There are 4 octets which display the IP addresses. For example, 0111 0101 100 10101 000 11101 and 000 00010. Second, decimal dotted notation. In this type of notation, the addresses are written in the decimal form with the decimal point or dotted separating the bytes. The decimal dotted notation is used to make the IP address more compact and easier to read. The value of each number in dotted decimal notation ranges from 0 to 255. For example, 117.149.29.2. Types of addressing. The concept of IP addressing is divided into two types: classful addressing and classless addressing. Classful addressing. In this type of addressing, the address space is divided into 5 classes: A, B, C, D and E. We can find the class of an address when given the addresses in binary notation or dotted decimal notation. If the addresses is given in binary notation, the first few bits can immediately tell us the class of the address. If the address is given in decimal dotted notation, the first byte defines the class. Class A addresses. In a class A network addresses, the first byte is assigned to the network address and the remaining bytes are used for the host addresses. The first byte of class A address is always 0. Now, we turn the other 7 bits all off and then turn them all on. We will find the range of class A network addresses: 0 0 0 0 0 0 0 0 2 0. This is the range. 2 0 1 1 1 1 1 1 1 to 127. The format of class A address is given as network dot host dot host dot host. Class B addresses. In a class B network addresses, the first 2 bytes are assigned to the network address and the remaining 2 bytes are assigned to the host address. The first bit of the first byte must always be turned on, but the second bit must always be turned off. If we turn off the other 6 bits all off and then all on, we will find the range of class B network addresses, that is 1 0 0 0 0 0 0 0 to 128, 1 0 1 1 1 1 1 1 to 191. The format of class B address is given as network dot host. Class C addresses. In a class C network address, the first 3 bytes are assigned to the network addresses and 1 byte to the host address. The first 2 bytes of first byte must be always turned on, but the third byte can never be on. Similarly, we can find the range of class C address as follows: from 11000000 to 192 110 11111 to 223. The format of class C address is given as network dot host. Class D and E addresses. The class D addresses ranges from 224 to 239 and is used for multicast addresses, and the class E ranges from 240 to 255, which is used for scientific purposes. Blocks. The main problem of classful addressing is that each class is divided into a fixed number of blocks, with each block having a fixed size. Class A address were designed for large organizations with large number of attached hosts or routers. Class B addresses are designed for mid-size organizations with tens of thousands of attached hosts or routers. Class C addresses were designed for small organizations with a small number of attached hosts or routers. A block in class A address is too large for almost any organization. This means most of the addresses in class A were wasted and were not used. A block in class B is also very large, probably too large for many of the organizations that received a class B block. A block in class C is probably too small for many organizations. Class numbers of blocks, block size applications are as follows, shown in the slide. Mask. The length of the net ID and host ID in bits is predetermined in classful addressing, but we can also use a mask. Mask is a 32-bit number made of contiguous ones followed by contiguous zeros, but this concept does not apply to classes D and E. Default mask for classes A, B and C as given below. Class binary dotted decimal CIDR as shown in the slide. Subnetting. If an organization was granted a large block in class A or B, it could divide the addresses into several contiguous groups and assigning each group to smaller network called subnets, or in some cases it can share part of the addresses with the neighbors. Subnetting increases the number of ones in the mask. Some important features of subnetting are: 1. Reduced network traffic. 2. Optimized network performance. 3. Simplified management. Class A subnetting example. Consider the following subnetted class A network: 10.0.0.0, 255.255.248.0 is equivalent to 81.81.5130.80. Then the addresses and subnet mask. Clearly 13 bits have been stolen to create the new subnet mask. To calculate the total number of new networks, that is 2n is equal to 230, that is equivalent to 8192 new networks created. There are clearly 11 bits remaining in the host portion of the mask. 2n minus 2, that is equal to 211 minus 2 equals to 2048 minus 2, and that becomes 2046 usable hosts per network. Supernetting. Due to fast growing of networks, time came when most of the classes A and class B addresses were depleted, but there was still a huge demand for mid-size block. A size of class C block with a maximum number of 256 addresses did not satisfy the need of most organizations. Even a mid-size organization needed more addresses. Then the concept of supernetting was used. And supernetting, an organization combines several class C block to create a large range of addresses. In other words, several networks are combined to create a super network or a supernet. An organization can apply for a set of class C blocks instead of just one. For example, an organization that needs 1000 addresses can be granted 4 contiguous class C blocks. The organization can then use these addresses to create one super network. Super networking decreases the number of ones in the mask. For example, if an organization is given 4 classes C addresses, the mask changes from 24 to 22. Example, let us say we have 4 IP addresses on the 4 LAN interfaces of our router 1.1.0.0 to 24, 1.1.10 to 24, 1.1.2.0 to 24, and 1.1.3.0 to 24. We want to summarize these network into a single route that can advertise across the WAN, which reduces the number of routes in the remote routers. We could summarize these routes with this supernet IP addresses 1.1.0.0 to 22. This single IP address references all 4 of the IP subnets. Here's a look at it in binary form. IP addresses 7 zeros 1, 7 zeros 1, 8 zeros and again 8 zeros. Supernet subnet mask 8 ones, 8 ones, 6 ones, 00 and 8 zeros. Notice the third octet of the supernet subnet mask, that is 6 ones 00. This allows the last 2 bits of the third octet to be any combination of 00, 01, 10 or 11. So, this supernet mask would show that any of the 4 subnets are available from the router. Classless addressing. Classful addressing is almost obsolete. Therefore, to overcome address depletion and give more organization access to the internet, classless addressing was designed and implemented. In this type of addressing, there are no classes, but the addresses are granted in blocks. In classless addressing, when an entity, small or large, need to be connected to the internet, it is granted a block range of addresses. The size of the block varies based on the nature and the size of the entity. For example, a house may be given only 2 addresses. A large organization may be given thousands of addresses. An ISP, as the internet service provider, may be given thousands or hundreds of thousands based on the number of customers to whom it is providing services. Rules for classless addressing. First, the addresses in the block must be contiguous, one after another. Second, the number of addresses in a block must be a power of 2, for example 1, 2, 4, 8 and so on. Third, the first address must be evenly divisible by the number of addresses. For example, the figure shows a block of addresses in both binary and dotted decimal notations granted to a small business that needs 16 addresses. Mask in classless addressing. In classless addressing, a mask is a 32-bit number in which the n leftmost bits are ones and the 32 minus n rightmost bits are zeros. We can say that an IP addressing, a block of addresses can be defined as x.y.z.t/n, in which x, y, z, t defines one of the addresses and the /n defines the mask. First address. The first address in the block can be found by setting the rightmost 32 minus n bits to zeros. Last address. The last address in the block can be found by setting the rightmost 32 minus n bits to ones. For example, a block of addresses is granted to a small organization. We know that one of the addresses is 205.16.37.39 to then we have to find out that which is the first and last address in the block. The binary representation of the address 205.16.37.39 to 28 is equals to 11001101 0001 0000 001 00101 001 00111. First address, if we set 32 minus 28 rightmost bits to 0, then it becomes 1100 1101 001 000 001 101 001 0000 or 205.16.37.32. Last address, if we set 32 minus 28 rightmost bits to 1, we get 1100 1101 001 0000 001 101 0010 1111 or 205.16.37.47. So, in today's lecture, we have discussed about the difference between the OSI and TCP IP model, and after that we will discuss about addressing of network devices. Thank you for watching.